Hello, and welcome to another one of my videos on the topic of management science, where we utilize Microsoft Excel to set up, model, and then solve simple everyday business problems. Now, my two usual disclaimers before we get going. Number one, I have gone ahead and built certain features into this blank spreadsheet, which you can download, and I'll tell you how to do that here in a second. Most notably, what I've done is I've taken certain cell regions and used the define name feature in Excel to give that cell region or those cell regions unique names. For example, if I were to highlight the salmon color cells under capacity, if I look in the top left, you actually see the word capacity. And that's because I have named that cell region capacity. And that allows us to use that more intuitive name in formulas and in our solver later on. So that's built into the spreadsheet. Number two, if you're watching this video on YouTube, please refer to the description below the video, and there you will find a link to the corresponding blog post for this problem. There I have the problem written out long form with full tables, and you'll be able to download this very file from the blog post, and you can download it and follow right along step by step with the video. So that out of the way, let's go ahead and dive into our actual problem. Now, this problem is a bit different than previous distribution problems I've done. In a lot of those, we've tried to minimize shipping costs and things like that. In this problem, we're actually trying to maximize the amount of product we can push through our distribution network. And here is sort of the background of this problem. We have a high-end car company called Ferrari Motors, and they're located in Stuttgart, Germany. Now, in the United States, their major market is the Los Angeles area. So we have movie stars and athletes and, all kinds of people out in LA that love their cars. But the LA office has had some recent problems, some high turnover and some drama and stuff like that. And someone along the way just forgot to order parts for the cars. So there are customers that have had fender benders or some part failure or want to maybe customize their car, but out in LA they have no parts. All the parts are produced in Germany and no one ordered them. So the new manager in LA calls up the home office in Stuttgart and says, "We need as many parts as you can send us, and we need them yesterday." So we are the managers in Stuttgart, and we are tasked with pushing out as much product to LA as we can. Now, as with almost all distribution networks, they only have a certain capacity. We can only push so much product through our distribution network. I mean, even an oil tanker has a finite capacity. The Federal Express 18-wheeler truck going down the interstate has a finite capacity. So shipping lanes have finite capacities. So as managers in Stuttgart, we have to figure out a way to maximize our distribution network in order to get the maximum number of parts out to LA and fast. So in the end, that's going to be our goal. This is a product flow maximization problem with a number of constraints. Because every stop along our distribution network, the shipping constraints will change. From city A to city B to city C, the capacity is not going to stay constant throughout our network. Now, the easiest thing to do in a problem like this is to draw it. I'm a huge fan of sketching out diagrams and models and things like that to help us visualize actually what this looks like. So let's take 5 or 6 minutes and actually draw this problem out. We'll have all of our nodes labeled and all of our arcs or shipping lanes labeled, the capacities labeled, and we'll actually be able to visualize what this will look like. So let's go ahead and do our diagram, and then we'll come back to Excel, enter our data, and solve it. Now, overall, what we're trying to do is ship as much product as possible from Stuttgart, Germany, which is the node on the far right, to Los Angeles, which is the node on the far left. So as you can see, there are 7 nodes, And we want to push as much product to Los Angeles because they need it, and they need it now. So let's go ahead and label our nodes. And I just want to tell you, during this sketch, I'm going to pause it while I do a lot of drawing, and then I'll restart it so you don't have to watch me sit and draw a whole bunch of stuff. So, okay, so let's go ahead and label our nodes real fast. The origin is Stuttgart, which is in Germany. Now from there, our product can go 3 places. And the one in the middle here is Bordeaux, and that's in France. And then up at the top, we have Rotterdam, so we'll call that RO. At the bottom, we have Lisbon, which is in Portugal. And then across the Atlantic Ocean, we have 2 nodes. We have New York, New Orleans at the bottom, and then LA, Los Angeles, over on the left-hand side. So I'm going to go ahead and pause real fast, and then go ahead and draw in the arcs connecting our nodes. Okay, so here the green arrows represent our shipping arcs, or our shipping lanes. Now note that they are arrows, so we're only shipping in one direction, therefore it is an arc. And let's talk a little bit about our nodes. Now Stuttgart over on the right-hand side is our origin. So what I'm going to do is I'm going to go ahead and fill that in with a color. We'll make that green, so green is go. And remember, LA is our stopping point, so we'll make that red. Now all the other nodes in the middle are transshipment nodes. So product is going to come into that node and go right back out, but it's not going to stop and sit there or anything like that. So it's a pass-through transshipment distribution node. So I'm going to go ahead and fill those in, sort of a yellow color. Now remember, for our shipping lanes, just like everything else, the thing that makes this problem the challenge that it is that our shipping lanes, our shipping arcs, the green arrows, are not of infinite capacity. We can only push so much product down each shipping lane. It's not infinite. In order to get as much product from Stuttgart to LA, we're going to have to work within those shipping constraints. So what I'm going to go ahead and do now is pause the recording. I'm going to go ahead and write in the maximum capacity of each arc, of each shipping lane, and then we'll talk about that when we come back. So I've gone ahead and drawn in the shipping capacity of each arc, or each shipping lane. Now, a way to think about this, and I know it's not the perfect metaphor, but you can think of our diagram as a series of pipes. And many pipes carry water. And smaller diameter pipes, say the pipes that carry the water up to your sink, are a lot smaller than the pipes that carry the water up your street, the water main. So a smaller diameter pipe can only carry so much water versus a bigger pipe. Basically, our shipping diagram works the same way. So we have smaller pipes of goods, for example, from Lisbon down below over to New Orleans, or we have very large shipment pipes with large capacities, for example, like New York to LA. The main complexity in this problem is built around the fact that our shipping capacities change as we go from node to node to node. And in order to push out the maximum quantity of goods from Stuttgart to LA, we have to take those changing capacities into account. Now, if you count the green arrows, you will see that there are 9. So that means we have 9 node pairs. So what I'm going to do is pause the video, and I'm going to go ahead and write down all 9 of those node pairs so we can see how our Excel model will be set up here in a couple of minutes. So we're just about done with our diagram. Now if you look on the right hand side, I've gone ahead and written down each arc or each node pair. Pardon the penmanship, my tablet does not have smoothing with this program, so it looks a little rough, so I do apologize. So we have 9 arcs, 9 node pairs. Now another thing to keep in mind here is that those are our constraints. So for example, from Stuttgart to Rotterdam, we're going to have a constraint of 50 units, and so on and so forth down the list. Each one of those pairs has a constraint per our diagram. Now another thing to note is that all of our yellow circles are our transshipment nodes. we're going to have a constraint in our problem that all these are going to be 0 because they're not holding anything. Goods come in and goods go out. These are not warehouses. They're just transshipment nodes. We have two constraints. We're going to have our capacity constraints, which are the labels for all the arrows that go with each corresponding arc. And then each yellow node is a transshipment node that will have to be 0. We cannot hold goods there. Given our model, let's go ahead and go back into Excel, set it up, and solve it. So as you can see, we have a fairly complex problem on our hands. We have 9 shipping lanes to consider, all with unique shipping capacities. We have 7 nodes in our distribution network. That is a lot to manage. However, luckily, with Excel, this is actually going to be fairly simple to solve. But first, let's go ahead and take a look at our spreadsheet and just talk very briefly about what each part of it is going to do for us. On the left-hand side, you will see our 9 shipping lanes or arcs. So Stuttgart to Rotterdam, Stuttgart to Bordeaux, and so forth. So those are our 9 pairs. In the salmon color row under capacity, that is the maximum amount of product that can be pushed through each one of those shipping lanes to the left of it. Now in the ship column in the light blue, that's actually what Excel is going to find for us. And if you notice, the column between ship and capacity is a less than or equal to. And that's because whatever Excel puts in the ship column, it cannot exceed whatever is in capacity next to it. Now down below in the pink cell, that's our maximum flow. Depending on what Excel finds in the ship column, given our capacity constraints, that will be the maximum amount of product we can push through this distribution network and still meet all of our capacity constraints. That will go in the maximum flow cell. Now over on the right, we have all 7 of our nodes. And what's important to note here is that Rotterdam, Bordeaux, Lisbon, New York, and New Orleans, remember, are transshipment nodes. So product is going to come into those nodes and then go right back out. It's not going to stay. So the net flow in those 5 nodes has to be 0 because no product is staying there. In the darker blue on the right-hand side under supply demand, you will see that for those 5 nodes, the value is 0. Now for Stuttgart at the top and Los Angeles at the bottom, those will be sort of opposites of each other. Stuttgart is going to put out the maximum amount it can, and then Los Angeles is going to take out of the network whatever Stuttgart sends. And then all that product will flow through our network and end up in Los Angeles. So we have 2 parts to our spreadsheet. We have our shipping relative to capacity, and then we have our supply and demand relative to each node. Now, a good thing about this problem, since I've already put so much into the spreadsheet by default, we don't have a whole lot else to do except enter a few formulas and then open the solver and then actually solve for our solution. Now, the first thing we need to do is enter a formula or a series of formulas into the net flow column. Now, I'm not going to go into a great amount of detail about this formula because I did that in my last video. So I'm going to go ahead and type it in, and then I'll briefly explain what it's going to do, and then we're going to move on. So in this top cell in net flow, we're going to enter a formula that looks like this. Equals sum if, so it's a conditional sum formula. Then it asks for a range, a criteria, and a sum range. So our range will be the from group of cells, which you can see it outlined it in a small blue line over on the left-hand side. So from, our criteria cell is going to be H4, and our range is going to be ship, which is the blue column there towards the middle. So what this is going to do is that it's going to go to H4 and find that value. In this case, it's Stuttgart. Then it's going to go over to the from column and look for wherever Stuttgart appears. So in this case, it's the top 3 cells. And it's going to take those top 3 cells and then go over to ship. And then it's going to add together just those 3 cells in ship and then place it where our formula is. So I hope that kind of makes sense. It's kind of looking up Stuttgart. We're saying, hey, Stuttgart is our criteria. Find that in the from column. And then wherever that corresponds to the ship column, add those cells up, in this case the top 3, and then put that in this cell. And that's how it works. Now we also have a second half here. And remember, this is a net flow, so we have to have some sort of subtraction going on. So sum if 2H4 ship. And the second half of this formula is going to do the exact same thing, except it's going to look in the to column. Now, we're not shipping to Stuttgart. We're only shipping from. So actually the second half of this formula is going to be 0 because we're not shipping from Stuttgart. But we'll go ahead and press enter. And there we go. Now it will say 0 for now because we haven't actually found the solution in the blue column, the ship column. So they will all be zeros until we do that. Now one of the beauties of Excel, of course, is that we can just drag all the way down and it will fill in each cell below it. So we have our net flow formulas. Now, believe it or not, we only have one more formula to put in, and it is ridiculously easy. And if we go down to maximum flow, where in this spreadsheet we're going to find out the maximum amount that is flowing out of Stuttgart? Where is that going to be? Well, that will be here in I4. So all maximum flow is equals I4. All right, so believe it or not, we have everything we need in our spreadsheet to go ahead and open up the solver and solve this. So we'll go to Data, Solver, open that up. Now remember, our objective here is to maximize our shipping flow. So our objective here is max flow, which is the same thing as the pinkish cell at the bottom of our spreadsheet. And again, we want to maximize our flow by changing the shipping cells. So ship. So we're asking Excel to find the values for ship that maximize our shipping flow down below. We do have 2 constraints in this problem, so we'll go ahead and click Add. Now our first constraint is on the right-hand side of our spreadsheet, and that is that the net flow for our transshipment nodes has to be 0. So we need the cells next to our blue cells to equal supply demand, because we name that region of blue cells supply demand. The cells next to it have to equal the blue cells, which are 0. Go ahead and click OK. The next constraint we have should be pretty obvious. We'll go ahead and click Add. And remember, our shipping values cannot exceed capacity. So ship must be less than or equal to capacity. Ship less than or equal to capacity, just how it appears in the spreadsheet. So we'll go ahead and click OK. I'm going to make sure that make unconstrained variables non-negative is checked. Our solving method should be simplex LP for simplex linear programming, and then we'll go ahead and click Solve. Okay. And it says solver found a solution. All constraints have been satisfied. Do we want to keep the solution? Yes, we do. So we'll go ahead and click OK. Let's take a look at what we got here. Well, the first thing that we will want to look at is our maximum flow. So given the capacity constraints of our distribution network. The maximum number of goods or products we can push through our distribution network is 150 units. That's it. It's like, water pipes that just can't take any more water or they'll bust. So in a similar fashion, our distribution networks just cannot handle any more. So we can only push through 150 units. Now if we look in our ship column, all of those are less than or equal to our capacity column, because remember that's a constraint we put on Excel. Now if we go over to the right, you will see that we have 150 units flowing out of Stuttgart, and then Los Angeles is taking those 150 units at the end. So net flow, it all cancels out to 0. As long as what Stuttgart sends is what LA receives, we're all good. And believe it or not, that is the end of our problem. So I hope you learned a lot. I look forward to seeing you next time.